So now in this video, I have a voltage booster demonstration. We have a power supply voltage of 5 volts right there. That was picking up stray signals in the air. 5 volts. Here you can see the capacitor is a little bit lower than that because we have a diode dropping a little bit of the voltage. But every time I get a good press of the button there, you're going to see the voltage go up. And I did set the probe to 10x, and also I set the meter to 10x right there. So you got to make sure the meter and the probe are set to the same setting. So times 1 or 1x and the probe, well, the probe at 1x would make the voltage drop a lot quicker. And so I set it to 10x right there, which we don't need to see anymore. So in any case, that's 1 volt per division. It's really easy to get up to 8 volts right there, which will be off the screen. So what I'm going to do is zoom in right there, and I'm just going to hit the right arrow. Now we got 2 volts per division. So now it's halfway right there. So each division is 2 volts. So we got a total of 16, and I'm not sure what the max voltage of this capacitor is. It's not going to hurt anything to plug it. Can't really see it right there. 50 volts. Okay. So yeah, we should be plenty fine. I doubt I can get up to 50 volts with this meter slowly discharging the capacitor. But that's the concern. So the higher the voltage we get, the quicker it'll discharge. But yeah, we can get up to 16 volts. It looks like pretty easily right there. It is kind of a struggle now. Higher voltage is going to discharge quicker. But yeah, there we go. So it's going to kind of discharge a little quick at first and then slow down a little bit. But yeah, we will set this when we get down about halfway. Yeah, it's going a little too slow right now. So I got it to 1 volt. It's still up there a little too far. I'm going to take this jumper and short the capacitor to discharge it. And I'm just going to do it quick, and then there you can see, boom, it went down as soon as I took the jumper off one end. Now it's back up to that discharge voltage. One thing I want to look at though, I'm going to press this, is how much current is flowing every time I press the button. About 28 milliamps of current. We get, there's resistors limiting current, but for the most part we get it pretty much uncontrolled. I'm going to yank the jumper, and then when I release the switch, inductive kickback is what actually charges the capacitor. So I just kind of want to get an idea of how much current we were getting when I press the button. So I really want to only press it enough for current to start flowing through the inductor. I want to end it at that point the best I can. And so physical switch, I'm taking a lot longer than the short pulse that I should be giving it. So I'll try to address that in future circuits. But this was just a demonstration for the voltage booster. We got 5 volts at the supply, but now we have more. Again, the oscilloscope in this case, whatever you're measuring it with, it's going to let a little bit of current leak through. So you want to minimize that as much as possible. But for demonstration purposes, this is just fine. If I yank this and we wait a little while, it's just picking up stray voltages in the air. The capacitor is going to self-discharge a little bit over time, but when I plug it in, there you can see we kind of picked up where we left off, and looked pretty good there. But now it's going down much quicker right there. You can see now when it made it across, we went down, you know, at least 1 or 2 volts. So now I kind of have this packet in the way. Just as a reminder, I'm using a 270 ohm. It wasn't written terribly well in there. I lost my 220 ohm resistors, but one of them was still on the board, and had a bunch of pack of resistors, and when I put the packs away, apparently 220 disappeared during that process, but I still had one on the board. So I'm using a 270 in place of one of them. Doesn't really matter. 220 is going to let a certain amount of current through it based on the voltage. This also has a little bit of resistance, and this other one, it's 270. It's also going to let, you know, almost as much. It's just a bit higher a value of resistor. Since we are thinking there's probably about 5 volts across there, I don't want to go lower than 220. 220 is the bare minimum. So I went up a little instead of down a little. But there's a little bit of resistance in the inductor. The one I'm using, other ones may not have hardly any. Be aware of that. So we have a situation. We saw the capacitor is naturally going to charge. So we saw that when I short the capacitor, then we had like current flowing. but then I stopped shorting it. I removed it. The voltage went right up to the supply voltage, 5 volts, minus about half of a volt. Because remember, it takes a little bit of voltage before the diode. We're just using a rectifier diode here. 1N4001. Doesn't really matter which one you use though. So it is going to drop a little bit of voltage coming through. You'll get about 0.5 volts more than you have over here when no current's flowing. It's going to build up like 0.6, 0.7 volts at higher current. Be aware of that. But in case, we saw that it got, a minimum voltage while we were just sitting here. Now we closed the button. And while I was closing the button, we got about as much current as you saw on the display there. I think it was like 28 milliamps of current with these two resistors. We're getting the current through that one, plus the current through this one. And then there's a little bit of resistance right there. So it lowered it a little bit more than it could have been. But in any case, I think there's like 25 ohms of resistance here. And so we had current flowing through there. And it takes a little while to get going though with the inductor, but virtually no time at all as far as our senses can pick up. So you could probably like measure it with an oscilloscope if you set the timing right. But it's very quick. I don't know how quick, but very quick. The thing is though, when you open the switch, that current does not stop. And so it was going through the switch because we already built up a voltage here while the switch was closed. We open the switch. Current does not stop instantly. There's a brief period of time. Again, it's very, very short, but it's going to keep pushing current. And then we got negative down there. We got positive over there. That's going to help a little bit with the pump. But in any case, it's not going to stop current. So this is a difficult path right there. It will raise the voltage enough to create a spark if we don't have this circuitry down here. But we open the switch. We do have this circuitry down there. So now we get a higher voltage here than what the capacitor voltage is, because it's going to push that current no matter what, basically. And so it pushes current that way, raises the voltage over there, and thus raises the capacitor voltage. So it depends on how much current is going through it when you open the switch, because that current's going to keep going, but there's a magnetic field that builds up when you force current through the inductor. At some point it's going to flow easily, although this does have a little bit of resistance. And when you try to cut that current, it does not stop instantly. It keeps flowing, whatever current you had going through it. But the current goes down quickly as well. But it can be pumped, in this case, into a capacitor to store the voltage. Now again, I had the meter probably set to 10 million ohms of resistance when it was at 10x, and probably 1 million when it's set to 1x. And you could see it was discharging the capacitor far faster than the capacitor was discharging by itself. It would go down by itself as well. But when we waited like 8 seconds or something, where I disconnected the probe and then set it back, it was basically at the same voltage as when I removed it. So the probe was definitely doing the vast majority of the moving right there. So you got to keep the process going, and whatever you're powering cannot take out more current than what you're pumping in. But the voltage will go up, so you can power higher voltages devices. You just need a lot of current coming in from the lower voltage to do so. It's mostly converting current into voltage, a lower voltage, higher current, into a higher voltage, lower current, as long as you don't have as much waste as we have here. You can get rid of almost all the waste, and then you'll have a pretty close to perfect conversion, maybe 90% or something. That's not unheard of. But usually you would just buy a module that does this. But still, it's a cool circuit. Maybe you will have something, instead of a mechanical switch, you use a digital switch or something. Maybe you will have something that you just have something really small that just needs a little bit of power, but it needs a higher voltage than what you are applying. You could set something up like this on your own if you wanted to. So, but still, it's more of a cool circuit than a useful one, because you can buy modules for like $1 that can move an amp of current. Probably an amp of current coming in, half of an amp coming out, but at twice the voltage out as in. Something like that. So any case, hope that makes sense. Rambled on long enough. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out links down below. They all help a lot. I'll see you in the next video.